So I think we can start the last class for the day. Quite tired as you, I guess. So let's try to make it fun. So in these 2 hours, we will try to see actually and try to actually address two main objectives on actually we can use machine learning. And in this sense, we are talking about model-based machine learning, as Ioannis presented us the very first day. So we are talking about physics-informed and thermodynamics-based artificial neural networks. And so the idea will be to see if and how we can use machine learning to robustly and reliably scale up, speed up simulations or problems that are quite computationally expensive, or eventually how we can use physics-informed thermodynamics-based machine learning to try to discover what actually we are missing in, I don't know, in our model, whatever model it is. So the idea is that indeed we would like to take the framework that Filippo presented this morning and try to plug it to the physics flags. So let me start with an answer. So prepare your laptop and will be fast, don't worry. So the idea is to go back to what we have seen in the introduction to regression methods. That is, we were having at certain moments the idea and the objective to see if we can find interpretable model. We have seen that sort of regularized regression model allow us up to a certain extent to discover some equations that are not so far away from the real equation. Though, we were having some noise. This noise was actually made vary at every position. So basically, this noise was normally distributed. So of course, the ultimate regression model was able at least to interpolate the correct governing equation. Then, of course, was not able to properly address the extrapolation. So the idea here is that we want to exactly have the same problem. So we have the governing equation of ballistic, very easy, exactly the same equation. So we have positioning, and we would like to train on the marker that you see on the half time that you see plotted here. So from 0 to 0.5 seconds. This part is this point, this now, it's more. Then yesterday, yeah, okay. This point we'll say like this. So we would like to see if we are able actually to obtain the original solution that is basically the integration. That's lovely. Okay, yes. The integration in time of the the classical ballistic equation, that is the second derivative of our displacement plus g equal to 0. And so we would like to train neural networks and these physics-informed counterpart. But before that, let's make a step backwards, really backwards, and go back to how actually we discover historically this kind of governing equation. So actually, what we started with, it was Niccolo Tartaglia, that in the 16th centuries was working and was hired by the Republic of Venice to run some experiments with some, of course, given goal, that is, of course, be the best to make war and conquer new lands. And so Niccolo Tartaglia started doing some experiments. Of course, now we can actually draw the trajectory of a cannonball. So you see what's actually found on the right. It was a quite nice sketch, especially if you think with today's mind. But what he found is basically that the trajectory of the projectile followed 3 parts. There is a first part that is linear. There is a second part that is sort of cubic. And then we have basically a free fall of a body like in the cartoons, where basically the object simply fall. And so this was the state of the art back at the time. And 50 years later, Galileo was not so in agreement with these findings. So what he started to do is some experiment. It was quite easy. It was having an inclined plate. Was putting some small objects that was simply let them slide and roll over this inclined plane. Then were simply falling off from this inclined plane. And it was finally trying to draw this trajectory. That is basically what they've done on the right. And the guy was quite hard and discovered that the trajectory of the object was following a quadratic law with respect to time. It was also the guy that said, okay, the free fall of the object doesn't depend on its mass, because this is what we were believing back at the time. And then, of course, as you know, well, 140 years later on, we had Isaac Newton that solved the problem. So the equation of motion are those that you find up on the right. We know what is the value of gravity, at least a good estimation of it, and so we can basically solve any kind of ballistic, at least without friction in this framework. So the idea here is to try to rediscover exactly the same governing equation. And so what we will have is we'll have a neural network, as we have seen just before with Filippo. So we will try to approximate the trajectory, the position. So it's u of I, where I denotes the time, as a neural network that is parameterized with respect to some parameter theta, that of course as input will take just the discrete time that's with which we acquire the signal. And we will do this by training for time that are between 0 and 0.5 seconds. Then we will try to train the same neural network, but that has been physics informed. And the physics in here is simply the Galilean physics. That is what we are imposing with the equation that you find in the parentheses. It's nothing else than the second derivative of the position in time needs to be equal to a constant lambda that we don't know. We will see if the model arrives to discover that. And so basically, this is nothing else that they were already knowing, Galileo was already knowing simple derivatives like this. So of course, if you integrate twice in time that equation of motion, you will simply find that u is quadratic with respect to time up to constant integration. So at that point, we would like to evaluate the prediction for later time or for the entire span of time. And then we would like to see eventually, but that's not needed, it's just a class to repeat the same two comparisons but using different activation function rather than hyperbolic tangent ReLU activation function. So, as yesterday, we have a QR code. Either use a QR code, either simply copy paste the URL. Tell me when you are ready. I'll follow you. So you will have the nodes. So you have the nodes. As usual, I ask you to duplicate. You can see here that's because I'm logging in with my account. Simply duplicate the project. You select the workspace as usual, and I'll wait 1 minute so that everybody, almost. For those that are there, they can already run the entire Jupyter notebook. You have the button where now it's written stop execution. You have run notebook. You can run it. We'll see together what happened. You're there? Yes, no, yes. In Italian, when someone doesn't reply, it means yes, so you're ready. So what we do is that we just import the classical thing. Important thing, as Filippo said, we want to select a seed. We want to select a seed on super NumPy because we will generate the data in NumPy. So what we've done is simply, of course, generate some data set. So I won't go really on that. It's not important for this enzyme. So what we have is, of course, our ODE that we want to solve. We will solve with some initial conditions, so initial position and initial velocity are equal to 0 meter and a velocity equal to 5 meters per second. So we do that in the block that is just below, where basically we integrate in time by solving this initial value problem. It's not really a big deal in here. You just need to know that, of course, we use the value G, that is 9.81 meter per second square, and that integrate from 0 up to 1, and we use 50 snapshots. So we will have 50 points from time equal to 0 up to time equal to 1 second. So of course, we generate the data like this. Then what we do in this block is that we are basically taking out of the snapshots. So the snapshot here is equal to 50, as we were saying before, and now we want only to train over the very first 25 snapshots, so from time between 0 and 0.5 seconds. So this is what we're doing here. We are copying this numpy vector into another vector that we call ti for the time and ui for the position. And then, as this would be too easy, we add some noise that, of course, is normally distributed, and that is equal to basically, no, there is no relationship. Okay, yes, you can think of this like the 20% of noise with respect to the it should be nothing. Yes. So it's equal to the noise that we add is randomly distributed and equal to 20% of the actual value of the position at each time. So as the position increases, the noise will increase as well. We can plot this, so this is what we're finding here. Indeed, here the noise is quite small at very initial time, but as we go with much bigger position, of course, the noise will be 20% of the value, the absolute value of the position, so it will be much larger. So at this point, we go to the neural network. So here done nothing. We go to the neural network. We won't normalize because, as you can see, sort of the value are quite good. We are for the x values for the independent variable between 0 and 1. That's fine. For the dependent variable, we are between 0 and 2. That's fine too. We can go on. And at this point, so we have a neural network that's probably is a little bit more implicit than what we've seen before. But basically, nothing else than before. So we define a class as a neural network. We define some parameter of this neural network. You don't really need to care a lot about this. Just care about, of course, we'll decide the type, the numerical type of a parameter. Our network that will be constructed with a construction. We will go to that later on. And this gamma is basically the lambda that we were seeing for the physics import. So we will be training this parameter, but not for the neural physics, I don't speak neural network. And then we have the constructor that does exactly what Philippos told us before. It takes a sequential and then it starts gradually to add linear with an activation, linear with an activation, and that's it. So of course, as you can see here, we have two possible activations, either the hyperbolic tangent or the loop, as we have seen already before in action. We set up also an initialization of the weights, just to be sure that, well, we normalize the weights, so basically bias everywhere equal to 0, and the weights are a normal distribution with mean 0 and standard deviation equal to 1. And then the forward path, that is how we make prediction, is simply linear predict, and the output of the neural network that we just constructed. So basically, we have our neural network that is u of theta, parameterized with theta, that are the weights, the biases of all the layers, and basically we would like to minimize the output of this u of theta given some t with the prediction of the dataset that we have already. So to do that, we create our neural network, the class, basically using the class above. What's important you need to notice is that we use as activation hyperbolic tangents, and that we use the inputs is dimension 1, the output is dimension 1, and we use two even layer with nodes equal 12. And then, of course, we apply the normalization. So in here, basically, you see the neural network. We start with a sequential that contains a linear that will have as inputs something with feature dimension equal to 1, that's the time. We will have as output 12 quantities that will then be applied to, on which we will apply hyperbolic tangents. Then we repeat this for another even layer, and then the final layer is a linear layer, so without activation function, where still the input is equal to 12.
and the output is equal to 1, where we use every parameter. So at this point, we can go to the training. What we do is that we use a random optimizer, you see it here, without necessarily going into the beta 1, beta 2, or the epsilon. We just determine the learning rate, so the LR that you see here. So it's a quite large and big learning rate, it's 10 minus 2. We train up to 40 epochs, that you see basically 40 epochs that are actually usually here, well, that's it. Don't look at this history, we will go eventually later on that. And so here is the training procedure. So we train over all epochs. This is to free all eventual gradients from the memory, as people was telling us. And so, of course, what we do is that we enter with our data TI in the noise between 0 and 0.5 seconds, and we make prediction U, Y, threads, and then we minimize the mean square error of this prediction with respect to the data. So what we are doing is we are using a simple and cumbersome batch gradient descent. Okay? This is storing some history of the parameter. Basically, we are just storing the L1 and L2 norms of the parameter as they evolve during training. It's not necessarily important right now. And that is just plotting. So this is plotting. So you can execute if you haven't already executed. So what will give us a system is basically the prediction of the neural network that are in black, continuous in time, with respect to the physical solution and the training parameter, and you see that quite rapidly the neural network is able to successfully feed the training data set, but as of course you can imagine, it cannot really extrapolate. Now these points, so we can plot the mean, this is the mean absolute error, so the L1 norm of the error in the interpolation and the extrapolation range. So quite bad in both sense, when we are talking about the non-noisy data sets, because the non-noisy data sets are basically the parabolic function that you see there. Okay? I guess we just plot the final results, so that's it. At that point, what we do is we do the physics-informed counterpart that I won't explain right now, because we'll see later on. The theory at least. So I just reinitialize the neural network with the same weights as before, and I simply launch the same procedure in training, and you will see now that the answer is quite different because the neural network is it's quite successfully in not overfitting all the noise that we had in the initial time instances, and actually you will see that later on it got perfectly. I don't know why it's not. It will get perfectly. I know why it's not. Sorry, a second. That's not okay. So at the end of the day, you will see that it's at the end of the same amount of stocks, so iteration of the boundary data set, the network prediction, that means the physics informed, is able actually even being trained on noisy data set to first of all don't care about the noise and also get completely the parabolic equation. Okay? At this point we can see of course we have 100 minus smaller in the final error with respect to the final solution, and then of course clear the fault. So what you can try if you want is to go up at the very beginning and change here rather than done and write relu. And you can run once more than not. Do you have a question for the moment? Of course, the question, what are pins, is not valid for the moment. I will explain you. What are pins? Out. So it's trained quite fast. So this is the classical neural network. You see the prediction is quite different. Actually, we will find sort of the scheme that Philippe will show us with the ReLU, that is sort of bias-wise approximation. And that's it, I guess. We have it. Yeah, that's the final prediction by wonderful. And then you have the pins that will do something else. And I won't show you right now. So I let you with the code running if you have it already, and I will go to the presentation. So what we have seen is that we compare the classical neural network, that is the one on the top, with the physics-informed neural network.
in which basically in the physics informed neural network, what we have said to him is simply that look, we are Galilean in mind, so we know that the trajectory is quadratic, and his second derivative basically the position is proportional to a constant, we don't know that constant, and just take into account this while you are fitting your data set. And as a solution, you can see that the physics informed neural network allows us very wonderfully to actually predict the good trajectory for a larger time, and of course, don't overfit noise that we put. And actually, what happened is that the physics informed neural network, so it doesn't know that G is equal to G, it thinks equal to a lambda, and yes?
And also?
And it discovered the value of lambda. That is, he simply discovered the value of the gravitational acceleration. And he discovered alone with these very massive things. So the messaging here is that if Galileo had used physics informed neural network, well, he would have discovered the equation of motion for ballistic 140 years before Isaac actually did. So this should pose to, well, a little bit interest you in the following lecture. Yes, two questions. I don't know who was first.
Does it work also if I have like the output the side of the samples that you use?
Yes, I think so.
Like two samples would be
You could do sample only, for instance.
one on the top and one on the zero. No, I'm just asking, I'm not implying
Try.
anything, I'm just asking.
Try. You are invited to try and try to answer to the question of Filippo. Yes, then.
You said you would have discovered the question of motion. So maybe I missed something. It looks like you did it.
I simply gave him, look, you find here, and the second derivative in time of u needs to be equal to a constant. I don't know that constant.
You know the acceleration. You imply
I don't know the acceleration.
no, that you know what the acceleration is, how it is defined. In Galileo, I'm not sure that you.
I mean, it's going, the Greek guy can tell you that already the Greek they were knowing that these simple derivation they were already able to come up with.
Galileo was not Greek.
Yes, but he read good.
Yeah.
So let's go to the theory. So physics informed machine learning. So what we have seen so far and what you might have in your heads up to far, after we have seen so different method of machine learning is probably this. And that's great. So this is the idea of data intensive model. It just needs a huge amount of data set and cross the finger, then the other way around you have the answer. Of course, and if it doesn't work, you just try to steer the pile until you get the answer. Allow me to explain this with some paradigm less, where we draw these two lines. So we have on one side the data from small, some data, big data, and the other way around, we have the physics that is inversely proportional to the amount of data. Usually, what we do, and what we have seen also during the workshop, we are here. We have very small data that are your experiments, for which you likely rate a model, and that's it. Okay, so you use a lot of physics, your model, some data to calibrate, those parameter, and that's it. Job done. What we do in machine learning usually is we are exactly opposite. So we are having no physics, we don't care about the physics. The physics might be so complex, so we simply don't know. We don't put necessarily a bias. At that point, we will need to use the big data. Okay, it's the case, for instance, in computer vision. So this is machine learning and deep learning, DL is deep learning. What we would like to do instead is to be and place in the middle. That is, we would like to use some data, as we have done, but also some physics, because we might be aware, we are not kids, we know physics. So why not using physics model bias, good bias, of course, up to a certain extent, in our machine learning model, in order to have reliable and robust prediction at the output. So this is physics informed machine learning, at least in a literature review. Of course, everybody has a different name, depends on the methodology. Here, I'm just trying to follow the paper that is in here, published in Nature Reviews, about what we call physics informed machine learning. So the idea in physics informed machine learning is that we have a machine learning model, deep learning model. Deep learning is just a subset of machine learning, so we can call it machine learning.
that have the prior knowledge stemming from our physical understanding of the world, and these deliver, well, of course, in principle, performance, reliability, and interpretability of the model that we define. How we insert this prior knowledge stemming from our physical understanding of the world? Well, there are sort of three categories. The first one is the observational bias, it's the classical one. This is the one that you do with the muffin and the dots when you train a convolutional neural network. The first thing you do is that, let's say that you acquire just an image of a dog, so you will just have one data, so that's fine. It's not good. So what you can do is that you can take the same image and try to rotate it. And so you will generate a lot of images. Then you can try to stretch it and all the rest. That is, you can try to augment the data sets with your observational bias. That might be some symmetries or additional symmetries or whatever symmetry you find and you have and you're sure of for your problem, and simply augment the data, and so the neural network will be able to see something, hopefully, from this data. The other way around is you have an inductive bias. That is, you are sure of something, you have a bias, might be what we have used for the second derivative in time of the trajectory. And what we do is that we write down the structure of the neural network, of the machine learning approach, such that it satisfies by construction that kind of bias, that kind of construction. And then you have the, I would say, the softer version of this inductive bias, where actually you, rather than construct the architecture such that it satisfies this bias intrinsically, it will be, and you will pass through an optimization problem. That is, you would like to minimize an error with respect to your prediction and what you believe that is the bias, the physical bias that you have. So what we've done is the learning bias for the pins, and these actually are the physics-informed neural networks, the classical, at least, implementation. So physics-informed neural network are nothing else than supervised deep learning, machine learning algorithms, but it puts physical laws that are governing data, and the evolution of this data can be prescribed by partial differential equation that you can extend to, in principle, a huge class of other physical laws, stochastic differential equation, and all the rest. So the idea is that we have a problem that we can generalize, and the equation one you see here is a first derivative design of a U, where the U is the what we don't know, in principle, the output of our network, as we have seen before, plus n gamma of U equal to 0. Now, this n gamma of U is nothing else than a non-linear differential operator that is parameterized by some parameter gamma. We are set to parameter gammas that we don't know. Okay? And of course, U is function in general of space and time, so x and t were the time. So spatial coordinate and time. So we can use physics-informed neural network to basically, yes, sorry.
So Filippo, just to make the connection with the previous one, and gamma is the second derivative of u plus lambda. Right?
Yes, that's it.
Equal to 0.
Yes, yes. So we can use physics-informed neural network to solve and address two goals. The first one is the solution of partial differential equation, and the second one is the discovery of partial differential equation. So for the solution of partial differential equation, what we do is basically we go back to the first and previous equation. Sorry, that is the equation one, where our nonlinear differential operator n of gamma is such that, well, its gamma is fixed. So we know gamma, so we have our partial differential equation formulated there in a generic form. And so what we do is that train a neural network, u of theta, that actually approximate the u that we want to find and satisfy that partial differential equation with gamma fixed, so we don't have any parameter. So the idea is what we do is that we will write down the partial differential equation we were having before, where we replace u with the approximation that is the neural network. So this will be the output of the neural network, and we call this residual. Okay. Of course, if you satisfy this partial differential equation, it means the residual is equal to 0. Now, how do you train a neural network like this? Well, you do as usual plus a term. So the first term, this is the loss function that we want to minimize, the gradient ascent, whatever as you want to. So we have the first term, that is what we call a supervised loss, that is basically the data. That is here we find the prediction of our neural network, minus the data that we have for that unknown, that will be our trajectory, and we try to minimize this. We have a multiplication factor, it's not really important, put this to 1, and that's it. To this, we add another loss, is what we call a supervised loss, where basically what we do is we try to minimize the residual. Okay, so that residual there, we would like to minimize it. Because at that point, if we minimize that, so residual equal to 0, we are satisfying those partial differential equations. What is important to notice here is this sum. So this sum here goes from 1 to nu, where nu are your data points. So in our case was a discrete time acquisition, while on the right you have NPVE. So these are what we call a collocation point. Collocation point, so it's basically where you like to evaluate the residual and minimize the residual to 0. So if we try to write it down as a neural network, you have some inputs x and t, so our spatial coordinates and time coordinates. You have a neural network that will predict us some value u. We will need to differentiate this u in order to compute the residual, and then we would like to minimize the residual. So in general, it will be, of course, they cannot go there, not necessarily equal to 0, especially at the very beginning. Of course, how we compute that residual, Philip already told us this morning, we use automatic differentiation. That is, you will have your output u of the neural network that is basically here, and now in that case, we need to compute the first order derivative in time and some nonlinear differential operator of that u. So we use automatic differentiation. Simple example just to refresh your memory. Imagine you have a function f that is simply the sum of an exponential plus the exponential square. Imagine that the first exponential is equal to a, where you don't know a, and the exponential square is equal to b. So what you do is that you build a graph, okay, that is basically here. What you do is that basically you take x, that is the input, this x you apply exponential, and will give you a, as you can see. Now you take this a and you square it, and will give you b. We agree on that? Great. And at that point, what you do is that your f will be simply a plus b. That's it. You got it. Now, at this point, you apply the chain rule differentiation, and that's it. You can do this numerically. So, automatic differentiation is nothing else than a numerical implementation of the chain rule differentiation. So, we do that to compute the residual. For the discovery of PDEs, what changes is that if we go back, we have the gamma there that we fix in the solution of PDEs. So, we know the PDEs, we just want to learn how to solve it. Now the idea is that we don't necessarily know the PDEs, we like to discover it, that is, we would like to find the parameter gamma. It actually goes exactly the same. What we will have is something, is just an addition here, the gamma in red, that is, will be looked basically as a parameter of the neural network. So it would be a required RADS equal to true, and the neural network will be able to update also that gamma. Okay? Yes, so if we go back to the example, what it happened is that the physics-informed neural network has encoded the u double dot plus lambda equal to 0, and it will find lambda basically equal to 10.1, something like this, with the data at the end of the training. While, of course, the standard neural network cannot simply go ahead and will simply nicely overfit, and so physically it will give us a projectile that then is floating in time, which is quite nice if you find something like this in nature. So this is just to show you actually how powerful is the introduction of physics, of a good bias in machine learning. Now the nice thing is that I ask you, not many of you have that, to use ReLU rather than the hyperbolic tangents in the activation function. So for both networks, we're having two hidden layers with hyperbolic tangent. Great. Hyperbolic tangent is the one that is on the top. And now the thing is that what happens if we use ReLU in the same architecture? So what you obtain is this one for the simple neural network. I change nothing else the activation function. Do you have any idea why this is happening?
Is the architecture same?
The architecture is exactly the same initialization, nothing changed except the rather than hyperbolic tangent ReLU.
So if we use more layer with ReLU, do you think it can be better?
Do you think? You want to try?
I think so.
You want to try? Can you try? Just you have after ReLU there is 1, 1 brackets 12, 12. So 12, 12 it means the node in each of the hidden layer. So you can put I don't know 24, 24, 24, 24. Right? Yes.
Because the first derivative of the ReLU is 1, whereas as we train the network, then the tangent approximates to 0.
Mhm.
That's why then we have this,
Yes, and then you are not. I feel fire, but
yeah, we
not
not really in the top of the core, the derivative is supposed to be zero, not constant as the value is.
the top of the core of the output. You're saying?
Yeah.
Well, but in principle, so we will have our colleague that will tell us if he puts more in the layer. You can see that's a discretization, and so you can look this still at piecewise approximation. Yes. Got it. So how we train a neural network? Great in a sense. So what we do is that we make some prediction. Let's go here. We make some prediction there. Okay. So this is our error because then we take the mean with respect to some data. So we have still our neural network. Then we differentiate this function with respect to our theta. Okay. So we take the first derivative in time, in this sense. So we take the derivative of lambda of L with respect to theta. And this will involve the first derivative of what is inside this thing. Okay? Now, in the residual, we were having, now here is just the first derivative. In our residual, we were having the second derivative in time of the output of the neural network. That is, if we go and apply the math in a very simplified case, so this is our neural network, basically it's an activation function G, as listed with Filippo. These are our parameter times the input that is time. Of course, when we compute with the automatic differentiation, the second derivative mathematically will be given like this. So the second derivative, the activation function twice times the parameter. And so if we go and try to minimize the loss on the residual, that is on basically on the second derivative of u, we'll see that we will find something like this, where here is not, it's an abused notation. It means that we have a second derivative of g, the activation function, plus something that is a third derivative. Okay? Now, if the second derivative of g, the activation function, is equal to 0, your loss, your gradient is equal to 0. ReLU, what is the second derivative of ReLU? 0. Everywhere. So we are not imposing at all any physical constraint. So we are not backpropagating the physical loss. So that's why it happens. So the importance of choosing good activation function and knowing the problem you're trying to solve. Nice example. We were talking about parsimony yesterday, today too. And we were saying that this parsimony, at least in the ballistic equation, was giving us not quite bad results. Now, what happens if we plot what we store in? We were having the Jupyter notebook, the L1, L2 norm of the parameter of the neural network in the case where we don't put physics and in the case where we put physics. So in the case of hyperbolic tangent, you see they are normalized. So between 0 and 1, the reality is not 1. So you see the norm 1, the norm 2 of the parameter, and in black, you find a neural network, the classical neural network, and the norm 2 and the norm 1. So it means that most of the parameter are at their maximum value. They have all probably the same magnitudes in terms of L1 and L2. If you look at the base, you see that basically we have a huge reduction of the norm L1 and L2 of the parameter. It means that the physical introduction, the physical bias, actually is inducing parsimony. The physical agnostic neural network is trying to overfitting, so it needs to update and change the value of all the parameter, while the physics-informed neural network, what it just wants to do is to approximate a quadratic function. And so it will act in that sense. But of course, you see now that if we pass through a loop, actually both they coincide. There is a minor change I don't really know at the very beginning, even if they are initialized the same, but the final converged value is the same for both neural networks, because indeed you are minimizing the same neural network with the same loss, because the derivative of that is equal to 0. Okay, so another important thing in pins is that if I go back to the formulation, even the discovery of the neural network, so what we do, and the trick here is to evaluate the residual, no matter what the residual is. In very complex problems, it might be complex, but that's fine. Automatic differentiation is great for that. We will need to evaluate in the collocation point, what we see in here called LPDE. So in our example, we generate bits, but not so much. And what we've done is that we put collocation point in which we evaluated the residual from 0 to 1,
and with a frequency that I don't want to compute because I'm too tired, so 20 points, 20 collocation points, 0 and 1, in which we will minimize with a 0. So we will minimize with a 0 even in this region where we are not having data. Now, what happens if we reduce the number of collocation points? So above is our results. Yes.
We can know where the collocation.
Give me 1 second. So here's 20 collocation points, what we were having before. Here you have 2, that is 1 at 0, 1 at 1. And here you have just 1 collocation point at 0. As you can see, the answers are quite different. The one with 2 is not so bad, still it's overestimating gravity quite a lot. We have seen especially with a black box approach without any bias. So it's thanks to the bias, of course. The problem is indeed the choice as we are solving every time, translate this to solid mechanics. A boundary problem, of course, will be dependent on how sample our physical solution in time, initial condition, and in space, so boundary condition. So this ends the first small talk on physics in neural networks. Yes. I don't know if Ioannis wants to add something. Yeah. Are you on?
Yes, actually, I have no voice. Normal. Well, we have planned to do the second part that will be on thermodynamics-based artificial neural networks. But unfortunately, with this voice, it's better to let Philip do it. Have also a conference next week, so it's better to save a bit the voice. Actually, what I would like to insist, though, is on the fact that we use these ideas to be able to solve boundary value problems of mechanics with a tremendous speed up of several orders of magnitude. But it enables actually to solve problems that before were not possible, where they were not possible to solve. But it's not only the speed up, the advantage. We have something else. You saw here with the pins that this physics-based approach allowed us to have a very good estimation, despite the noise of the gravity. If we take this idea by enforcing the physics of the laws of physics, what we target here is, and because we talk about constitutive modeling, is to have access to some other intrinsic properties of the materials that we are about to study and get new knowledge from this. But new knowledge means that, of course, now it is in pregnancy, all these theories. I think that in the years to come, we will see more and more things. This new knowledge will be combined with existing knowledge. So I expect at this point to rediscover with what we know, with a more automatic way, the machine will rediscover what we know. And maybe the next step is that it will show us, yes, but for this kind of materials, this kind of property is also emerging, it's important. So, Philip, please. Yes.
Continue. Yes, press please. It's great. 1, 2, 3. Yes, great. So we are moving towards constitutive modeling. So the idea is that rather than solving the boundary problem, we want to find the constitutive model representation. So right now, rather than plugging physics, we will be plugging thermodynamics. Of course, what I eventually need to say is that this work is part of the ERC grant co-wing, BI without voice. So the idea here is that we are targeting complex material, of course. Here is not so much complex, especially for this community. Sound is quite fine. If we start working today, it's going to be quite more difficult. So the idea is that we are dealing with multi-scale material, with multiple physics, multiple characteristic inherent scales, and we'll write down an realistic constitutive model of this. We have some good, I would say, people doing this in this community, but it's not quite numbers. We are wondering, should I take the fabric, which fabric should I take, and should I take and characterize the breakage, should I do, so, well, it depends. So the idea is to, of course, try to reach the scale, because of course we have this material, but at the end of the day, we like to avoid landslides to come to the spot without any problem and bus or car. So the idea is to try to pass and acquire some information on the microscale and then solve macroscopic problem. course, to do that, it's quite easy. We know some maths. These are the rigorous asymptotic homogenization theory of mathematics, in which basically what we can do is that we can simply, by studying the solution at the unit cell of our characteristic microstructure, we can then actually solve the boundary problem at the macroscopic structure. So what we do is that, imagine you want to solve a boundary problem at this macroscopic scale. What you miss in this equation is a nice equation, closure equation that is a constitutive modeling. We don't need this in multi-scale simulation, because what we do is that for every Gauss point, if you're relying on a displacement-based formulation, like finite element, what you will do is that you will take your strain field and stress and strain increment, and you will simply use it as boundary condition for another problem where you have your own microstructure. You solve this, what we call the auxiliary problem. You come to the volume average stress and stress increment, and you can go back and solve in implicit problem, would be nice, this boundary problem on the macro scale without actually having to deal with the characterization of the constitutive behavior of that unit cell. Now, however, this this of course brings us to the Fe square, Fe dem, Fe what you want, and is quite detailed representation of the response of the material from that emerges from the micro scale and goes to the macroscopic scale. However, this costs quite a lot, especially when we start dealing with huge scale and take the last slides, I don't know, probably it's not 1 kilometer, it will be less than 1 kilometer. But when you start having microstructure like this, should be somewhere, not the scale, but this is quite smaller. So if you need to characterize the material at this scale on that large scale, well, it's going to be extremely expensive. And the fact that especially with multi-scale, what happens is that you need to solve for every Gauss point. This is a theoretical. That is quite highly nonlinear and expensive. And you need to repeat this for all Gauss points. You do dynamics, landslide, you need to repeat for all time steps. Do implicit for all increments. So it's going to become quite expensive. So the idea in the last year has been to try to accelerate this by using actually neural network that use some data at the microscopic scale of auxiliary problem. We use this data with some strain as inputs and of course the characterization of the state of the material, and as output we will have incremental stress that we will use that to solve the boundary problem without actually needing to transform any more to the solution of the auxiliary problem. However, the problematic in here is we've seen with the classical example for the black neural network, the one in red, is that we will come with a poor reliability of our prediction. How can you be sure about the prediction of the neural network? You might not be able to generalize well. We have seen that we were having a projectile that was floating in time wonderfully physical, so we are not able to generalize nor to extrapolate. And in general, when we start dealing with quite complex material, that's only from the mechanics point of view, but we might have multiple physics. At that point, we'll need really a huge amount of data to learn what is inside those data. So the idea is to actually leverage some physics, thermodynamics. So here I would like to talk about thermodynamics-based artificial neural networks. Of course, you might think to use the pins as well for this problem. The definition is quite a little bit different because at that point you will need to put the pins here, that is over the solution of the auxiliary problem, rather than at the level of the constitutive mode, where you will solve that about the variable. Okay. So thermodynamics-based artificial neural networks. First, thermodynamics, a little bit. So let's consider a solid with Doctoral configuration B, and we write down first line the energy balance, where E is the internal energy, dot is the rating time, P is the first Kirchhoff stress tensor, F is the deformation gradient, Q is the referential heat flux, and R is some heat source. Then you can write down the entropy unbalance, that is this inequality, where you have the production of the entropy production rate that will be given, and depending on the entropy rate, and well, T there is the temperature, okay? So at that point here, we are basically recalling what has been introduced from the seminal point of view by Coleman and Gerting. At this point, what you know is that we can combine the two expressions and obtain what we usually call equals to have inequality. That is basically, we know that the energy production rate needs to be bigger or equal to 0, second law of thermodynamics, and then we actually, by substituting, we obtain a form like this. Where here, what we have substituted that rather than taking the internal energy rate, we define its Lagrange transform, that is the free energy, the element free energy. At that point, what we can do is that we can assume, of course, that this flux and this will always be equal to, actually, we won't be considering this, it's much easier. We won't be considering like this because finally we'll put ourselves in isothermal condition. But even that, what you can see is that actually this will always be positive. So, well, you can simply reduce the closure inequality to this bigger or equal to 0. And what you find in there. And then at that point, of course, we were interested in the characterization of the response of that unit cell. So what we need to do is not simply characterize the stress at the local point of that cell, for each of the point belonging to the cell, but we want to characterize the volume average response of the unit cell. So what we do is that we simply take the volume average over the unit cell with periodic boundary condition and anti-periodic fraction vector that will simply deliver basically us the same equation where we have this superscript y, where basically the superscript y means the volume average quantity of that quantity over the volume v.
You will find as a result of the periodicity of this material.
So the principle is
so at this point we continue. So we have the closest term inequality. I will drop out all the y because it's quite looking at the question. So everything from now on is volume average. And what we continue to do so is that we follow once more the seminal work of Coleman and Gerting. So we assume that our free energy, Helmholtz free energy, is a function of some quantities. You find it there. The first is the deformation gradient, so our deformation measurement, temperature T, and an additional state vector, Z, where these Z's are what we call the internal state variable. So the internal state variable, we introduce it to characterize basically the all these phenomena that happen inside this volume in which we are averaging, and they're basically related to irreversible phenomena. One other solution is what's also, I think, constant from the very beginning he presented. It was to this come actually to it's a second school from the fact of eventually characterizing the state of the material by looking back in time to the coupled stress and strain. Okay. If we have this internal state variable, of course, we need to come up with a dynamic evolution of this state variable. It's the evolution equation that in the general form will be written as a function f we ignore now, that will be a function of the state variable and the internal state variable. At that point, what we do is that we have our phi. In our equation before, we were having phi of theta. Here it's easier, phi of theta, phi dot, sorry. So what you can do is that simply differentiate that free energy. So you get this. You agree on that? Okay, well, what's more? Right. This, sorry, here is a contraction. So this is deep psi over the f, deep psi over the t, and so on. And at that point, we can keep this inside the closure theorem inequality. Okay. So the basically the dissipation rate equal to this, and basically we will see that we will find the definition of what a thermodynamic admissible process is. That is a process for which the stress is the partial derivative of the energy with respect to the deformation gradient. Something very similar with the entropy. This is conjugate with respect to the temperature, and then we find that the internal dissipation rate, mechanical dissipation rate, is simply given by the product of what we might call sometimes thermodynamic stresses, that are the big pi there, and the rates of the internal state variable. At this point, of course, what we know as more is that we have also the second law. So this is the first law of thermodynamics, and we have also the second law of thermodynamics that is basically allow us to say that the internal dissipation rate must be non-negative. For more information, I invite you to look at the book and the slides of the two previous doctoral school of thermodynamics and constitutive modeling. So now at this point, we know we refresh our memory to the maps. We can go to see what are these stuff with thermodynamics-based artificial neural networks. So in the PZ, we have exactly what is in the course. We have a psi, and this from the side we can compute anything. and we have the evolution equation. Great. So this is what we do with the plan. So we have first one on top. So we have our input that are the state variable and the internal state variable. We have a neural network that we call on the right a psi of theta at the neural network that will predict the value of the free energy. Then we differentiate automatic differentiation, this with respect to the input, and we call the first derivative above equal to the. Someone is waiting for two. What is that? The first one. Thank you. That's right. So that's our the stresses. Second is the entropy, and the third one is the internal dispersion rate. So what we do at this point is that we minimize, not necessarily this loss. We can talk about that later on. So what we minimize is a loss related to the error with respect to the prediction of the free energy, and so free energy data, if we are able to measure that, forget that for instance, and then what we minimize is the difference between the stress data that we know, we measure, and the derivative of that the network with respect to F with all the other gradients with respect to the dissipation, and to this we add a regularization loss, like in pins, is a sort of residual, where these are basically is the minus the Marconi brackets, that is basically we take minus the dissipation needs to be equal to 0. And if it's not, we put a loss term. So we will have an error that we may minimize. Now, just a small thing, we don't really need to minimize this term of this term, or even this term. Of course, if we are isothermal condition, there is a need. But this term and this term are not needed in reality to satisfy the first and second order. Because in reality, you can see easily, you don't need any loss in the prediction of psi because you're training psi from the derivative. So you can characterize fully a function from its variables. Okay? And then of course for the dissipation rate, you don't really care about learning what is the value of the dissipation rate. What you care is just be able to predict the evolution equation. We will see this in a second, and that this product is positive definite and will be given by that function, by that loss. And so the second ingredient is that indeed what we were talking about, the evolution equation. So what we do simply is imagine that you acquire the rates. So in discrete time, for whatever you want, for discrete time experiment, but also in numerical simulation of your internal state variable. And so you just want to learn this operator where apparently there is a theta here is missing. So it's a neural network that predict this rate. Okay? Yes.
Just one question. The L reg, why do you need the norm? Is it need a scalar?
The L, sorry?
The L reg on the left, the brackets max and 0.
I don't mean it.
Okay,
Just that it's no problem. The mean of the square of the thing or the whatever.
Okay.
So it's not a real norm.
Yeah, sure. Now
It's not a norm. Yeah, that's why there is nothing. It's not norm P. It just.
no, it's just a
But
scalar.
yes, indeed.
Yeah.
Indeed, it's scalar. So I should not need a norm. I simply need to compute the volume average, the mean of that term, and put it in my loss function, compute the gradient, as the book is telling us, and that's it. Now, the question would be, is that up to now we assume that, well, we know this guy here, the z, and of course we can also compute the time derivative of this z, the internal state variable, but in reality, if we go continue a little bit more, so of course here's a spoiler. If you go back to our material, this one, I would like to do an exercise with you. So please take your smartphone. I would like you to participate. So I have a question, just a question, it will be super easy. You can change your name to be anonymous, that's okay, it's fine. There is no prize, fortunately. It's fine, can go. Okay, so the question is, what are the internal state variable of this material? Where this material is this one? Go on. Only? That's it.
configurational entropy. Okay, so again, I love the taste. Where is the taste? There is time, color, history, size, friction angle, distribution, we don't know what, porosity, amount of dust, lovely, friction, different possibility, lambda after, and shutters or C, very great. So I think we can stop. So the idea that I wanted to prove, but then of course you went to a joke apparently, is that, well, you might ask to the best expert in this community, and they might be probably not agree on what are the internal state variable for this piece of material. And sand is quite a standard material, we agree. So the idea is, can we find somehow this internal state variable by looking at the microstructure of this material? So I just think from the title, the answer is yes. So the idea is that to do so, what we define is a new quantity. Don't bother yourself with the name. Is what we call the internal coordinates. So the internal coordinates is nothing else than the all those quantities that allow us to describe a piece of material and their degrees of freedom. Okay. So if you are thinking to simulate the same sample in the EM, of course, this will be the displacement field, the velocity field, you might have some contact forces, the force network, and so on. That point, the idea will be to see if we, from this microscopic structure that lies on a high-dimensional space, we can project into a low-dimensional space and derive the constitutive model that is characterized the stress and all the rest from this state variable that we project into a small dimensional space. So the idea is that basically, indeed, we assume that we can find the internal state variable Z by applying an operator mapping H, not yet defined, to these internal coordinates xi. Of course, this is true that this is Z if your free energy, that is your stress and all the rest, depends on the Z that you just found. And at that point, you can also say, okay, yes, without too many assumptions, I can also infer that the existence of a G operator that is not the activation function before, sorry for the same symbol, but it's nothing else than a pseudo inverse of the H, that is, we can enter with Z in this operator and we project back to the internal coordinates, where this small field represents actually and simplify the low rank representation of the same side. That is, we admit that we have a small error in these operations. So basically, what it tells us is that give me the xi, my structure, and I will project the H into a small dimensional space that will call this Z, but then in G, I can take Z, and put it back in the microstructure. So of course, then quite easily, you can as well find the evolution equation of those Z simply by time differentiating the two operators in both sets. Okay, I won't spend so much on this. Now, the idea is, of course, how you find this operator H and G. Of course, sorry, as I mentioned, you can derive the dynamics, this you can compute this derivative in here if these operators, these functions are, well, they're differential. Okay? Easy peasy, we're gonna approximate these two functions with neural networks. So they're gonna be differential. So that constraint is not approved. What we're using in here, I think Noel talked a little bit about this, but just roughly about autoencoder. Correct me if I'm wrong. Great, thank you. So what is an autoencoder? Is an unsupervised machine learning algorithm. The idea is that you have some inputs, you have two bunch of neural networks, and the output should be equal to the inputs. That is, you don't need label, you just have feature, and you want basically to enter with this feature. And a neural network that will have a small dimension at the end, the output layer that is quite small, and then another neural network that take this small thing and try to reproject it, reconstruct the xi, so the original input. Okay? Of course, so this path basically from the minimization of a loss, where this is not a norm, that is basically the xi, that are your data line minus basically G applying on H of C. That's it. Okay? That point, what we do is that so this will give us a compressive representation of the internal coordinates of the microstructure that we can then of course use in the previous formalism of the term to infer completely
the stress state and the evolution of the Z. Okay, this pass through the minimization of something that completely will resemble like this. But once more, you can remove this, you don't need it. You can remove this if you don't need it. If you're isothermal, you remove these two, and that's it. So what we come in here is that we have found from the internal microstructure of the material and its representation, degree of freedom, we found a bunch of variables that allow us to describe the stress from that and eventually also reconstruct the same microstructure. And of course, predict and find constitutive load. The nice thing about this is that now you want to make a difference. We have seen we want to make prediction. To make prediction, you won't need to carry all the way the xi, because you don't need to bring with you the internal state variable. If we go back to the multi-scale simulation, you just need the z, because you want to predict the stress, completely increment the stress to solve your binary variable. So at inference, what you will do is that you will simply reason in terms of z, that will be so on the right part, to predict the evolution of the z, and so predict the evolution of the stress. So actually, you don't even need the second two derivative, you just need the first one, stress, that's it. What you can do though, so basically this formula here is written down here, so we enter with temperature, deformation gradient, state variable at time 0, we predict the stress, we predict the rate of that evolution equation, we simply integrate, we solve these initial value problems for the z, and then the nice thing is that at any point we can take the z that we predicted, the dynamic of the z, and decode them into the z, that is reconstruct the microstructure. There was a question? Yes.
Okay. Can you example how you go about to dimensionality?
Sorry, I lost the last part.
Getting the method how you choose the dimensionality of the z?
Yes. So the dimension of the z, how many z do you need? So the easy way we have seen with laser regression is that you could take and put there actually the same dimension of the z. So it's actually a neural network that is not actually a funnel, but it's actually just a rectangle, and put the penalization of the amount of the z that are different from zero. So the system will try in a sense to compress at maximum the z, and you don't put like it's quite cumbersome in that sense. Then if you have a feeling and you were saying, okay, I want 6 because whatever, you can put 6, but you can pick up, you can let him pick up. So simple example, just to show you why we are bothering with all of this. So why time and not time? So why not classical neural network? So simplifying assumption, we don't have at all any microstructure. We assume that we know the state variable. In these above example are the plastic deformation actually. We assume that we are in thermal material processes, small strain fragile, and on the left and on the right you see two different materials. On the left is a microplastic material with isotropic compression and extension side of it. On the right, you see an hydroplasticity model coming from inside. It's not signed, by the way, nice. With some strain-driven rush too. So the comparison interesting in here is between the blue and the red. Blue is ANM, so time with the thermodynamics. The red is without thermodynamics. So what we expect from this volumetric isotropic compression, which is materials, right? We expect that basically the stress are linear, so we stay in linear elasticity, and you see actually how the normal neural network, the red, start to accumulate cement as we start to slide back and forth. The nice thing is that if we take these stresses and try to evaluate with a good energy, the analytical expression of the energy for that material, we see that it's not even satisfying the first principle, that's why we don't stress, and we can plot the dissipation rate. And you will finally discover that you're able to create energy, it's a neural network without thermodynamics, with your series of negative dissipation rates. So you are producing a huge amount of energy from nothing, which would be great. That is probably thing. And then the same you have in hydroplasticity, where we rapidly lose the without thermodynamics. Yeah.
Just to be sure, so here you run a dissipation, you train on network, and you just try to.
Yeah, not with this data, I train around the data, and then this is, yeah. Okay, here a little bit more difficult problem, even if it's quite easy. So what we have is still a uniform material. So we know the internal state variable. Though this material is rate dependent. So we have Persina type viscosity. And so here you find basically the prediction for unseen loading path, where basically what we are doing, I think, is a biaxial. Should be a biaxial, I think. And so we are basically starting with larger amplitude in the strain. We can see that we can follow, sorry, I missed the legend. The legend is there. So continuous line, the reference model behind, prediction are the dots. We can predict basically everything. Nice thing to mention for the thermodynamics guys in this room is that we see that the dissipation rate is not linear because we are basically rate dependent. That is something that the model find, the neural network find from itself. The nice thing as well is that we can predict the rate effects. So these are basically the same loading path, a simple shear, but with different gamma dots. And of course, what I forgot to mention is that the prediction, even if the model has been trained on a discrete time acquisition of the response to the material, the prediction are continuous, time continuous. So we are not dependent on the increments of our deformation, which was quite a big deal for machine learning in the constitutive model some years ago. Another material with some damage. Okay, we have plasticity and damage. You see once more the prediction should be something like concrete implementation in Abacus. We simply generate data in Abacus, and then we steal their constitutive modeling by simply learning with the machine learning. So now we can build another software with their constitutive model. I will explain later on. Is
Side of the train, the double.
strain back out. By Irish is gonna be difficult. I don't remember. We are less than 10,000 in principle. It's a full three-dimensional material. And what we do in this case is that we generate data sets randomly because it was just our proof of principle. So we are not generating particular strain path. We simply enter with a random strain rates, and we have a constitutive model behind to generate the data. We will see something different later on in our model. Example. We agree about this.
Yes, I have a question. So let's imagine that you have this prediction for each loose point, and then you have a structure. Then you want to get the equivalent of the structure through a Newton loop, for instance, what you want. How do you manage that? Did you trust the gradient of the distance?
It will be later on.
Okay.
Well, if you're implicit, you will know if you can trust him or not. Agree? If you have an implicit formulation.
Yes.
If you converge, you will trust implicit. Up to what tolerance, because it doesn't not review the sign. Yeah, so we'll see later on.
Or maybe you can insist on the last one.
Is that we are dependent on the particular time step or strain increment. So of course you could do like you will be forced in Abacus in this case to go very small strain increment, or you can do simply a huge strain increment and you want.
So basically, you don't need any something, well, the whole.
Yeah, the whole problem of the peak if it's not smooth, dodge, that's perfect. Yes. Sorry, I will go with it. Yeah.
Yeah, could you just help me understand how you capture the unloading part? Like, can you also unload at different intervals?
Yeah. You see there. You see there. I unload a lot of times. Like it unloads randomly. It's not here in the paper. Some of the paper is there. So the unloading here is not a problem because if you learn properly the evolution of these internal state variables.
Okay.
Yeah, so that's it. You don't fit the stresses.
You don't fit in with the stress. So it's not a sort of like you accumulate every time because you are the small error in the stresses before and then you bring it up at certain points. You will slow.
You learn the energy.
Yes. There is no treatment. No. Yes, definitely.
So the problem is that neural network in general, the feed-forward formulation we have seen at the very beginning with Filippo this morning, they are not SO3 invariant. So they don't respect those group of symmetry. Though there are some other approaches like graph neural network, and if we know them, is what you basically use to train self-driving car. They, in their structure, they are SO3 preserving. So your answer will be invariant that. Then there are some other people that try with learning invariance. So you can learn everything in invariance, so you will respect that symmetry. The problem is that when you go to finite elements, you want your vector. So if you have invariance, either you assume coaxiality, which is quite problematic, especially for Geomaterials, or otherwise you are not able to solve the vector. Right? You could also try to simply rotate all the links. No? That's fine. You can do it on the fly as well. Zero computational cost. Do you agree you want to show this later on if there is time?
You have 35 minutes, so
35 minutes.
do as you want.
Do you have time? Do you want to look at the code? This? So either use guides, you don't need to scan it, sorry. Sorry, you don't need to scan it. You were having it ready. You have the pin and zone. You just need to go to the time and zone. Here is a very simple example just to show you how things work. So we know the internal state variable because otherwise it might take some more time, especially with the other folder. Okay, this is nothing else. What we import is basically the data set, and we have a simple one-dimensional hypoplastic material that is basically here. Now, what we have in all here, we have just a stress, and we have a discrete time acquisition as we want to compute the rate of our state variable. We need to have a t plus delta t and a t in order to use whatever t plus delta, whatever you want, depending on scheme. Here is a simple first order approximation forward in time. So what we have is what is a time plus and a t plus delta t minus, but that's not really a problem, just a discrete time formulation for the data set. So these allow us to compute that finally from our z variable, that are the vars here, the z dots that we'll be minimizing later on. Here is for you if you want to try some noise. I haven't put it here. Actually, probably I can execute the notebook if you want. Yeah. So what we do is nothing else than what you see before. Is we split everything in nothing. Yes, indeed. Sorry, I implemented very cumbersome. So I think I take. Yes, I split just the data set into training and validation. Okay. There is no test because just to show you the approach. So what interests us, we'll see later on, not all this quantity, I'm just bringing that with me. What we do here is that we find the normalization parameter for epsilon dot, sigma, z, and z dots, okay? Then you have the neural network, which might look nasty, but it's not. So what we have is nothing else than two neural networks that use the constructor as we've seen for the pins. The first one is neural network psi, is the one that will predict the energy. And the first one is the one, the NF, that will predict the evolution equation. So this is the construction we were seeing before, we don't really care. And now here we have two functions that are normalized and standardized. So these, they simply apply the transformation we were seeing in feature scaling yesterday morning. So we have a feature, we want to scale it, so we remove a beta parameter and we divide by alpha. And for the normalization, we basically do the inverse transformation. This will be important when I will go back to the to how we compute the gradients. Then what you do is that imagine that you want to predict the energy. Yes, so we have to block two forward block make prediction. The first one is for the energy, and the second one that is basically here is for the evolution equation. Probably I should zoom.
grades. So for the energy, what we do is that we enter with some inputs, and these some inputs are here, okay? Don't care about if inference folds. I was trying to be concise, but probably might be more problematic to follow, but don't follow. Imagine that we are inference equal to fold. So here is when we are training, okay? When we are training, so we enter with inputs for which we require to be able to compute the gradients, okay? So the parameter of the neural network for the psi are of course requires grad equal to true, but we want also the inputs to be able to be differential. So what we do is that these inputs actually is nothing else than the normalized epsilon, the normalized z, and the z dots normalized. That is not really important, but it's important if we want to have the penalty constraint in the second law of the thermodynamics. So what we do then, this m so means normalized. What we do is simply we denormalize this quantity, okay, inside the neural network. And then, so skip the else, we don't care. And now here what we do is that, okay, so we have normalized variable at inputs, we denormalize it inside the neural network, now we renormalize it. It's quite smart. Do you have any idea why we are doing this? You remember yesterday the exercise that we managed to do with Shankars? We were having tau and gamma. The code was normalizing both of them, and then you were asked to predict the shear moduli in gigapascal. Though you were having the prediction in the normalized. So in the normalized, you will not be able to define G as the derivative of tau normalized with respect to gamma normalized. That's not G, that's something else. So what you need to do is basically every time you need to do the chain rule differentiation we were seeing yesterday. Okay, I won't write it down in here. So either you write this explicitly when you want the stress, because remember, we have the psi, the energy, that is function of epsilon and z, that are normalized because neural network one normalized, so it will output normalized psi. Now we want to compute the real stress. The real stress is not the derivative of normalized psi with respect to the deformation that are normalized. So what we are basically doing here is that writing down this chain differentiation, chain rule differentiation, we are simply saying to the network, hey, look, as we want to have the stress, and the stress is the derivative of the energy, the real one with respect to the strain, the real one. So what we do is that we let the network see what is the link between the normalized quantity and the unnormalized quantity. Because this percentage is the success rate. That is, to predict the normalized energy is the only thing that we can predict. We need to have the normalized z and normalized psi. And at that point, though, we need to not denormalize the energy. Here is not denormalized because we don't know the energy. We are not minimizing the energy because we don't need, so we don't know what are the parameters to normalize. So this is quite easy. If you know the energy, you will need to denormalize the energy. And at that point, you want to compute the gradient of the energy with respect to the strain. So the strain are where? So this would be the derivative of the energy with respect to the normalized energy. One. The derivative of normalized energy with respect to the normalized strain. Something is the derivative of the network. The normalized strain, the derivative of the normalized strain with respect to the strain. That's it. So you will compute the good stress in a good measurement without actually doing explicitly this chain rule differentiation. Of course, you can do if inference also train. You can also compute the dissipation rate. So it would be the derivative of the energy with respect to the z multiplied by the dot stars, so z dots. And you will have also the normalized stress and the dissipation, for which you don't know the scale. And for the evolution network, you will simply enter with the input and the rates of the z. We call the neural network with, for the evolution equation, we use one hidden layer with 64 nodes and GLU activation, while for the psi neural networks, for the energy, we have one hidden layer, once more, with 2 power 4, so 16 nodes with subclass activation. And then what we do is that, okay, just normalize and convert everything to tensor because these were NumPy array. It's not a very big deal. We define the input, so we have the two
training, one for the neural network that represent the energy, and the other the evolution equation. So we just created two set of input to do two training. What we do is that we define, okay, we'll do 10,000 epochs. We will print the error every 50 epochs, and we have a learning rate of 10 minus 3. Now we have the neural network that we just created, we were seeing before. We have two neural networks. The class of neural network has module, has two neural networks. We would like first to train the energy and then the evolution equation. So what we do is that we freeze the parameter related to the neural network of the evolution equation. That is basically we iterate over the parameter. Philippe was saying us, these are all the weights and biases of this neural network, is the evolution equation. And we set their required grad equal to false. So you won't compute the gradient with respect to this parameter, so they won't be updated. We economize a little bit of money in that sense. Loss function means per error, add them as before, learning rates 10 minus 3. We iterate as before, so this will predict the energy and the dissipation. So at that point, what we want to do is that we will have a loss with respect to the prediction of the stresses and the stress value here, plus the penalty on the non-positive dissipation rate. So we want to penalize if we get no positive value, that is negative value dissipation rate. So what we do is that as the dissipation rate might be of any value, and we don't want an error that might be of the order of 1,000 or whatever, what we do is simply we normalize the dissipation rate by its maximum over the batch. We multiply this minus 1. So if this minus 1 is smaller than, so it needs to be positive, so that's it. Okay. So it basically, if we were doing without the minus, we apply remove to the dissipation rate, we will have 0 error when dissipation rate is negative, okay, and an error when dissipation rate is positive. We don't want that. We want to minimize when we predict dissipation rate are negative, so we apply the minus. That's it. And then the same thing backwards. Yes? No, was question? Right. So while we train the thing, it will train. So we have trained the psi. Now we freeze the psi parameter and we activate the z parameter for the evolution equation. So we train that thing quite fast. You can try to run it. And then we evaluate the error. So here is the error in the stress for the test dataset that we haven't used for validation for nothing. Quite small. Is the mean square error? Yes, the mean square error. Sorry. We plot. So yes, what I forgot to say is what we have used for learning. Path. It's the first path that loads in fraction and then unload to 0 stress, and another path that compress and then unload to 0 stress. Okay, so these are our training days. Okay, the error for the evolution equation of the z. The z dots, they are basically the same as the sigma, pure coincidence, and we don't care about that. And then what we want to try is to predict the responsible material for another loading path. So we load basically our initial stress, basically, but also the entire path because we like the error for that new path. And then what we do is that simply what we do. Okay, so what we have over there. Okay, now look at those distortion tensors because we are working with NumPy array and then the TensorFlow PyTorch wants to have their tensor. So what we're doing in here is probably I need to go down a little bit. Okay, what we're doing in here is that we initialize our system material at 0, state 0, for instance, and what we iterate over the time step. And what we do, so we predict the z and the sigma in the next increment. How we do that? Very easily, not very precise though. What we do is that we call this function, perform constitutive increments. So what we do is simply we solve initial value problem, okay, with some initial condition. There are basically the z at time 0 or time z, that is the actual one. And after we have successfully integrated the z using from the evolution equation, that should be there. So this is our input. So this is just pre-processing to convert everything to tensor PyTorch tensor. These are our prediction. So this will predict the z dots. So this function will simply predict the z dots given something.
And these functions of MEP inside by will simply integrate this up to the time that we want. And once we have the bars next, that is the Z next, we of course can predict the edge side next. Here we are strain rate independent, so it's simply the sum of the two, and then we can predict the stress next. And we leave everything. So we are basically our constitutive model done with a simply resolution of an initial value problem. And then we can plot the thing. So the shaded, I see from there, the shaded is the reference solution, and these are the stress versus steps item. What we do is we start doing compression, and then we'll do some multiple cycling, and we can see we can follow without any of the error. And the same for the Z, where the Z here are the plastic deformation. Do you have a question for the code? Well, it's fine. But there are lots of details on these in different applications, and you have my contact. So if you want to discuss, we can discuss later on. So probably going to be the lecture. So now let's go to the easy part, the complex part. So this I need to say nothing actually. But yeah, so in the case of heterogeneous material, we don't necessarily know the internal state variables. We were saying we might be able to discover that using our stakeholder or other dimensional interpolation technique. You select the number of internal state variable. As we were saying before with the question of constants, we can simply put an initial guess is quite big for the number of state variable, and then put basically an L1 minimization on this output. So most of them will drop to zero. Simple example, for just a proof of principle for lattice materials and lattice plastic. So what we have is the polymer description of different kinds of material, where we use as internal coordinates, so the microstructure that we encode to obtain some state variable. We use the displacement field and the internal forces at the bars. We don't see, because it's so nice, the shaded thing is the polymer response for new dataset, while the continuous line are the prediction on the neural network, stress, energy. You see here the variation of some of the state variables that we discover. Should remember use something that is elastic, plasticity is actually related. And here we see basically the
What is the material of the bars?
I think you still told me this. With some hardening, I don't remember. Yeah. So we can take the Z that we which we describe the material stresses, and they code them. So basically use that operator, the G, and we can rebuild the full microstructural field. Here is quite easy, just the internal forces and the displacement of all the nodes. The nice thing, as you could imagine, is that running that thing takes a certain amount of time as we increase the size of the structure, while of course we don't feel that using the neural network. Here is not really important, and this is important when you go to the multi-scale, so the live value variable. A pedagogic example, just to be more accessible to the community over there. So the idea is that we want to have EM simulation of a general material, and so let's consider this as our what we call in a very new fashioned way a virtual plane, that is a virtual representation of the reality in the planetary code, for instance, or an EM simulation. So what we use is a sort of in principle, it would be nice as the problematic with this kind of material when we go to multi-scale is the selection of the RAV, the representative elementary volume. So the idea would be rather to resort to statistical ensemble method. So the idea is that you would like to have a statistical representation, stochastic representation of your representative elementary volume. And so the idea is to run actually smaller stochastic elementary volume. So every time they are different and their position every time is different. And then at the end of the day is that using Monte Carlo, the Monte Carlo methods, you would like to converge to an average response that will lead basically to the identification of the RAV. For more, don't ask me, don't ask to the guide or to Jean Student in Paris. What we've done is simply pedagogical, so we just took 3 stochastic elementary volume, so there is no convergence in the sense of the current simulation, just to let you see that if we just already take only 4 elements, you see that the average is already quite smooth. These are grain triaxial compression, monotonous and cyclic, where the shaded are the multiple SEV, and the average is the average of the observer. So what we're doing here is that we take the displacement field of this, we take the average of this, so we have a virtual average of the twin, and we try to learn the response of this thing. So first we will have the average displacement field of all the grains, and these are our internal limit field. We'll only be using that to see if we can find some state variable that allows to retrieve and characterize these two behaviors. So it's very simple behavior, much more richer in reality, but at that point, you might need to span with much more data. There is no point in just to show you how it works. So the idea is, of course, to try to learn this behavior and discover the state variable. So to show you, so we have 4 bunch of monotonous logging paths that are basically like that one, but a different initial confining pressure. So these are the gray lines. So we train the network over this line, okay? And now we simply try and ask the network if it can predict for something that is lying within this range. So we are checking just the interpolation capability of the network. You see these plots, so this is QP, and here you got in Q inside the toric, the new prediction for a single impact, which is quite smooth and quite representative of the system. The nice thing is, of course, when we pass it to cyclic, for cyclic never seen, and the model is quite good at predicting this value, and especially this nice returns that we retrieve. So you will tell me, of course, you retrieve it because you are having, I think it's 2,000, 4,000 particles, so you're bringing all this rich information. As we don't have so much time, so rapidly we can take the Z per se, and that's like here, predict the position and recreate basically statistical. This doesn't provide lots the displacement, but we can repeat completely the microstructure and compare it with the virtual twin. What you see here, where basically on average we have a good answer and a good variation of the position of the grain in our sample. Is the volume average once more. Rule pass to previous scale. So the idea is, of course, this is sort of can help us to one day see if we can discover something, but of course, what
Sorry,
the other.
Before you were producing the displacements of the grains, of all the grains in the sample, based on the evolution of the
Z, so
of the
for variable, I have their dynamics quite easy, and then I simply have the operator that I found before, and I apply to this. So it will simply, I will apply the inverse, yeah, then it will simply recreate the microstructure. Yeah.
and compare it with the exact one.
Yeah, that's it. Yeah. Fine. Okay, so the idea now is to go to the last part, is how can we speed up multi-scale simulation. So let me take the simple example of the lattice, as it allows us to well, have a proof of principle. So the idea is here that we have, I don't know if you can see, we have multiple lattice cells. We just train the behavior of one unit cell. We learn it, which we've done, and now we simply using asymptotic homogenization, we perform the simulation that is homogeneous, I mean, with one given constitutive law in the macroscopic scale, where the constitutive law is simply given by the homogenization of the response of the unit cell that is with that, and we compare with the reference solution. Here we are applying the CDF version, either only inelasticity or up to plasticity. So there we classify. And here what you see is a quite classical result in synthetic homogenization, that is, as epsilon decreased, epsilon is the relative size of the unit cell with respect to the size of the structure that we are analyzing. That is, if we are asymptotically going towards an homogeneous material, well, you see that basically the prediction that are the is of the reference solution, that is a real case, the U epsilon is in blue, will converge actually to our homogenized model using thermodynamics-based artificial neural network. Same happens for the energy, and same happens also for the dissipation in the case of inelastic floating path. The nice thing is here is to compare the computational cost with respect to the reference case. So on the left, you have basically the computational cost ratio. It is a quantification we come up with to compare the two models without necessarily optimizing both the detailed finite element simulation and the one on the left. So we are simply seeing how much each of the Gauss points, how many times the constitutive law is called, and you find the relative errors. It allows us to have an increase in the population of the order of 300% or 40, depends on the loading path we are really going up. Then of course we can do cyclic loading path. So here we are taking the same structure, just version on one side and the other side, version on the other side, and releasing it. So what we do is that we go first torsion. First torsion up to 30 degrees. Clockwise, anti-clockwise, we go up to 60 degrees, 50 degrees probably, 50 degrees. We come back, we load up to 60 degrees, it is down there, and then we release the structure. We go back to some permanent position because, of course, we accumulate plastic deformation. And the nice thing, of course, dissipation-wise, it's fine. Nice thing is here is to see and observe the variation of one of the internal state variables of the system found. And this should allow us to see if we have, and we are able to represent the reversibility. So blue means 0, red means different from 0. So we go, we make a little bit of torsion, and then we unload. There, the reference model tells us you remain in elasticity. So we expect that when we unload, we are 2. Okay. So we are not characterizing elasticity. Now we load on the other direction, we go a little bit of elasticity. So when we unload up, we have a little bit of plastic deformation, and then the same when we unload the bigger torsion angle that we have the inelastic deformation up to there due to warping of the structure. Rapid transit phenomena is just the same thing that we have in transit phenomena. So it's a stochastic material behind steel type of lattice. What we do is that we apply a force, the shear force is there. The protocol is this one, so incrementally up to a point, we keep a little bit the loading with quite small time step, as we are dealing here with shock impact, and then we are putting the force to 0 and see what is the response after stabilization time. So here is basically the response, the formation response, the form shape at the when we arrive to the maximum shear force that is basically in a shear displacement where this is a vertical displacement is here. Okay, now we keep this point a little bit, so we move there, we are accumulating, and now we unload. Oops, sorry, we unload, and that's it. We have some permanent deformation. The nice thing in here is actually to see that here the state management was simply the microscopic deformation, plastic and total of each of the bars composing for our lattice structure in the unit cell, that simply like this. So after DC, we can decompress them as before, and so we can plot actually what we see in here is the evolution of the microscopic total deformation, plastic deformation in the intradose of this cantilever beam. So you see that basically the x and y axis, look at x. So 0 is in the middle, there is minus, and here is positive. So we are compressing up there, okay? So we have the microscopic deformation in compression, where there we are applying the force, and you see basically that we are first loading, that is this plot, then we unload, we increase the deformation, and we unload and we release the total deformation. What is quite interesting is actually to look at when we decode plastic deformation. So we are loading, we are here, now we relax, we accumulate some other plastic deformation, and now we release completely the loads, and we have an increase of plastic deformation, and you can simply check this curve with the upper one, this is the total, this is the plastic, that's minus this, to give you the elastic in principle, and you will see that we have some elastic deformation that has been trapped inside our panel. That is, we are able basically to come up and find with the model the elastic energy trap phenomena. It's quite classical one, but quite zero short cost. So I'd like to conclude and look at the movie with you. So just the conclusion are, well, we have seen two approaches, thermodynamics and physics for neural nets or machine learning, whatever you want. So they allow us to have and move actually towards an implementation of machine learning that is reliable, robust, and eventually scalable. The idea in physics inform, we have seen that actually we could have discovered ballistic equation well before Isaac if we were using pins. Because there's a joke, just to tell you that this is something that will allow us to bring innovation in today's science. And for time, well, we have seen quite many things. I won't go too much into detail. The nice thing that you need to remember is we are able to, they allow us to speed up quite a lot, otherwise computationally prohibitive simulation, wide scale simulation. And I think they open together with all the physics machine learning model the possibility to interpret what we have been looking at so far and questioning about how we model this material. So sort of trying to learn this behavior and then back analyze what we just found and see if we can implement that in sort of what we were missing. But I think if you want to play with the code, in addition to one that you have in the deep notes and GitHub of the Doctoral School, there you have it, just type my name. So I think that if you have a question, we can have a question. Otherwise, thank you for your attention. And sorry for the very kind of time.